So now that we've talked about all our sort of qualitative ways of determining whether particular ions are present, and briefly touching on some quantitative techniques like precipitation reactions, we're going to now switch over to a far more accurate way of determining the concentration of particular ions that are present in our samples. So now we're going to use sort of machinery to help us find more accurate concentrations of our sample solutions. Now the good thing about this is, because we're using, sort of pretty high-tech pieces of equipment, you probably won't have to do these as praxis school. So a lot of this stuff is understanding the theory of what the components of the machines are and why we have these components, and then how to interpret the output of some of these machines, right? And if you're lucky enough, you might go to certain universities and have a practical day where you get to use some of these machines. But in terms of how you're going to get assessed on this, it's primarily going to be sort of in a theory exam. So we're going to be looking at a concept known as spectroscopy. And so for this section, and even with the next section, we're going to be focusing on different types of spectroscopy. And spectroscopy is essentially a very, very general term to describe the interaction between matter and the electromagnetic radiation. And what electromagnetic radiation is, it's just anything on the wavelength spectrums. You can utilize UV or ultraviolet radiation. You can utilize infrared radiation. You can even utilize our visible sort of light spectrum. Okay, so that's what electromagnetic radiation is. Now, the first type of spectroscopy that we're going to look at is a process known as calorimetry. And calorimetry relies on the fact that different solutions are going to have a particular color, and the more concentrated a solution is, the more concentrated that color is. It's almost like cordial in water. If it's really, really dilute cordial, then the color is quite light, right? But if it's really, really concentrated cordial, then the color is quite dark, and we're going to use that property in order to detect for the concentration of certain substances in our sample. Before we jump into that, there is something that we sort of need to understand first, and that's, so when we see color in real life, we have to understand sort of where this color is coming from. And essentially, the color that you see is actually not because that object is emitting that color, but it's because it's absorbing all the other colors, and the only color it doesn't absorb is the color that you see. So for example, if you see, the green plant leaves, so the chlorophyll in plants, which give it its green color, don't actually emit green light. What they do is they absorb the opposite of green light, which is all your purple and your red colors. So because they absorb all those colors, the only wavelength of color that's left is the green color, right? So that's why you see green for plants. And that's what we call complementary colors. So we're going to utilize this concept in a sec to help us determine concentration, right? So this process is called calorimetry. We'll draw the diagram for calorimetry first, and then we'll talk about sort of the main components and what they're used for, okay? So if you just copy these diagrams down, okay, so these are sort of the main components in a calorimetry sort of setup. The first one is you're going to have a light source, okay? And so the point of the light source is just to provide sort of a beam of light, right? It's going to be sort of white light, obviously, and so it's going to have every single color of our visible light spectrum, right? Remember Roy G. Biv, red, orange, yellow, green, indigo, violet, whatever, right? Roy G. Biv. It's going to be a combination of all our different colors in a white light. But if our sample solution has a particular color, we want to pick what we call complementary color, which is the wavelength that color absorbs the most. So what I mean by that is, if this sort of sample solution is green, for example, then this object here, which is what we call a color filter, we want a purple color filter. So it's almost like a slit with a bit of cellophane through it. And what we want is we only want the purple color wavelength to pass through it, right? I'll go through sort of why that's the case in a sec. But so this thing here is called a color filter. And the key thing with the color filter is we want it to be the complementary color of the solution, okay, of our sample solution. So we want it to be the complementary color of our sample solution. So going back to what we said before up here, right? If you have something that's green, it absorbs all the different colors in our visible light spectrum, but the one it absorbs the most is the exact opposite of that color. It's the complementary color. So for green, the complementary color is purple. It absorbs purple the best, right? And remember, we said it's green because it absorbs everything except for green. That's why it looks green, right? So we want to pick the wavelength that it absorbs the best. And so we said it's complementary wavelength, which is purple in this case. So what happens is only purple light gets shone through, right? Only purple light gets shone through, like so, okay? And then what's going to happen is we're going to detect the amount of purple light on the other side, and then you're going to record that, right? So this is just a recorder. It's pretty much, it's normally going to be a laptop, but I thought I'd just draw something fancy there, right? But it's essentially just going to record all the data for the color that's been absorbed, okay? So if I shift this up and then we'll go through it. To sort of recap what happens, because this is quite tricky to sort of wrap your head around at the very start, is you have a light source which has all the different wavelengths of color, like red, blue, green, etc., all our different colors of the rainbow. And what we essentially want to do is we want to pick a particular color that our sample is going to absorb the best, okay? And the general rule, if you're doing it sort of manually, and we'll go through like a better way in a sec, but if you do it manually, you would just try to pick the complementary color for your sample there. So if the sample was green, you'd pick purple. If the color was red, you'd pick blue, right? That kind of thing, right? And they're not sort of, exact opposites, because color is a spectrum. So you might have like sort of a mix of color, but the idea is you pick something as close to the opposite side of the spectrum as you can. And that's because if it's green, it absorbs purple / maybe red light the best, right? And you want sort of the wavelength to come through that it absorbs the best. And so what happens is when this purple light gets shone through, because only now the color filter only lets purple light through, now this sample is going to absorb some of that purple light, right? So this sample is going to absorb some of that purple light, and only a fraction of that is going to pass through to the detector. And so what's going to happen is I'll sort of change that to a dotted line, right? What that's saying is that not all the light gets shone through reaches the detector. Only a fraction of that light is going to come through and reach the detector because this sample has absorbed some of that light, okay? So depending on the concentration of this sample, the higher the concentration, the more it's going to absorb, right? Because the stronger the color, the more it's going to absorb. And so that's why at the detector, you're going to detect less, right? And you'll correlate that with a certain concentration. If you have a really dilute sample, then it's not going to absorb that much of this light. And so therefore the detector is going to detect a high signal because there's not that much absorbance, and that's going to correlate it with a particular concentration, okay? And so that's why, because it's based off how much this sample absorbs, we want to pick the color that's going to give it the best chance to absorb. And the color that gives it the best chance to absorb is the complementary color, okay? So if we go through sort of the main components of calorimetry again, to solidify what we've talked about, the first thing is our light source, okay? Our light source, and the point of the light source was to produce the light to be absorbed by the solution, right? To be absorbed by the solution, okay? And then what happens is we pass that through a color filter, right, to get a specific wavelength / color of light, okay? Because when we have a light source, it's generally white light. It's going to have all the different colors mixed in together. So we pass it through a color filter to get a specific wavelength, or sort of what we see is a specific color of light, okay? And then the second thing is what's known as a transparent cell, okay? Transparent cell, which is essentially to hold the sample, our sample, and we need it to be transparent because we need the light to be able to pass through for it to be absorbed by the solution, not by the actual cell itself. So that's why it's a transparent cell, to hold the sample. And then the third thing is a detector. And the point of the detector, like we said, was to measure the intensity of light. Intensity of light. And the fourth thing is a recorder, just to record all our data, okay? And so those are the components of our calorimetry setup. We have a light source, we shine the light through, we pick the wavelength or the color of light that our sample is going to absorb the most, and that's our complementary color. So that passes through, our sample is going to absorb it, and depending on the concentration, it will absorb a particular amount. So in here, we'll just make a note, if it's high concentration, it's going to be high absorbance, and as a result, it's going to be a weak signal at the detector, right? So if it's high concentration, it's going to absorb a lot of that light, so it's going to be a weak signal at the detector. Then if it's low concentration, right, it's going to be less absorbance, right? Because there's not that much color to absorb it, less absorbance, and so that therefore it's going to be a stronger signal at the detector, okay? And then that's going to record it, and it's going to give us some sort of output. And so if we look at the output that we get, you're going to get an absorbance number, right? All it is, it's just going to give you a reading. It's just going to be a number. And that number means nothing if you don't have things to calibrate this machinery. So what we're going to look at now is a calibration curve, which helps give meaning to this absorbance number, okay? So what a calibration curve is, it's essentially a series of standard solutions. And what standard solutions we've talked about before? They're any solution with accurately known concentrations, okay? So they're solutions of accurately known concentrations. And we need these to create what we call a calibration curve, right? So we need these standard solutions to create a calibration curve to give our absorbance number meaning. So what we mean by that is with our standard solution, so let's just say the example is nickel sulfate, right? You'll create solutions of known concentrations at different intervals. So here it's intervals of 0.1 mole per liter. And then you'll put them into the machine and see what absorbance number you get. Okay, so this is sort of the output here. So we put a 0.1 mole per liter solution in here, and we got an absorbance reading of 18. We put a 0.2, we got an absorbance reading of 0.34, etc., right? So we put these into the machine. We know the concentration. That helps us plot a calibration curve. And so we're going to try and have a go at drawing a calibration curve here. So the axes of our calibration curve are absorbance on our vertical axis, and absorbance doesn't have a unit. It's just a number that you get off the machine. So absorbance, and then you're going to have concentration, right? And it's in moles per liter, right? As our standard SI units are, right? Now then we're going to sort of plot it out, and you can sort of measure our equal intervals here, but just for the sake of time, we'll do that quickly. So might be something like that, 0.1, 0.2, 0.3, 0.4, 0.5, like so, okay? Etc. And then you might do it sort of in intervals of 0.1, so it might be 0.1 all the way up to 0.2, 3, 4, 5, like so. I won't write them all in. No, maybe 1.0, for example, like so. Okay, and generally absorbance only goes up to about 1.0. Any number that's beyond 1.0, you can get a measurement that's beyond 1.0, but it generally gets a bit less accurate after that. And that's just because of the calibration of the machinery, right? Nothing that you need to know for sort of year 11 and 12. Now, how do we plot this curve? So remember, these are of known samples. Like we know the concentration of these numbers, and we know the absorbance reading of these numbers off the based off the machine, right? So at 0.1, it's 0.18, right? So it'd be like sort of like here. Okay, 0.2, that's about 0.34, so it's about sort of here, I'd say. 0.3, we said it's 0.49, so sort of up here, right? You sort of get the idea, right? 0.4, it's 0.66, so it's sort of somewhere here. And then 0.5, it's 0.81, so it's probably somewhere like I'd say right here, right? And obviously my graph is not the best, but you get the idea. And you got to sort of see, like, it's a very linear trend, which makes sense, right? As you get more concentrated, there's a greater absorbance, right? We absorb more of the color because it's more concentrated, yeah? So once we draw this, once we plot these points, the idea is you'll then draw like a line of best fit. So then if we draw a line of best fit like that, it should look something like that, okay? Now it's freehand, so it's obviously not the best line, but that'll do, right? So this is what we call our calibration curve, right? This is our calibration curve, right? For, nickel sulfate or whatever it is, right? This is a calibration curve. So this is before you take your unknown sample, you have to come up with this calibration curve because the machine spits out absorbance number. That means nothing if we don't know what that absorbance number correlates to in terms of concentration. So you take your known concentrations and you find out what the absorbance numbers are for each of those concentrations. Then once you get a reading, you will be able to find out what the concentration actually is. So for example, having a sample like 0.35 absorbance reading, we can simply go to absorbance. 0.35 is probably, I'd say, about there, right? So 0.35, so just above that point there, right? Then you draw a dotted line across and then come down like so. And I'd say probably that's about 0.21, maybe 0.22 moles per liter, right? So our sample one 1 we said is, let's just go 0.21 moles per liter. Yeah. And sample 2, let's just change this absorbance number to, I don't know, let's say 0.92. I think that's what it should say on your booklets. 0.92. If we change our absorbance rating to now 0.92, for sample 2, 0.92, if you notice, it's 0.81 is the last absorbance reading we took. So we've sort of got to extrapolate it a little bit, and we'll talk about that in a sec. Right, so if that's 0.92, my graph's probably a little bit off, right? But the idea is it's beyond our last point, okay? So we've got to extrapolate like so, okay? So we extrapolate like that line out, and then we draw a dotted line down, like so. And I'm just going to say that looks probably like 0.56, okay? So it'll be a lot more accurate if you have grid paper, but just eyeing it, I'd say it's 0.56 moles per liter, okay? Now, to go through sort of how this correlates with this setup here, well, essentially what we did firstly is we got 5 solutions of known concentrations. We put it into this position here, shone the light through, picked the right filter, and then detected it, had a list of absorbance numbers. So this is our output here. Then we plotted this graph. And then after that, what we did was we then put our unknown sample in here. We put our 2 unknown samples in here, passed it through, and then got our absorbance reading for those 2 unknown samples, which were 0.35 and 0.92, okay? And then once we had those absorbance reading, then we came back to our calibration curve and we looked at the absorbance on the left-hand side, and then we took that across to the curve and then found out what the actual concentration was. And then we wrote that down there, right? So before we sort of talk about, which one's more accurate, just a couple of things to note. It's always absorbance on the left-hand side because the absorbance is your dependent variable, the concentration is your independent variable. So the absorbance is always going to change based off how your concentration changes. And then when you get a reading, you're getting a reading for absorbance. So you're always looking at the y-axis and then bring it across to find out what your x value is. Okay, very commonly, because absorbance and concentrations can be like sort of very similar numbers, as you see here, they're like 0.3, 0.34, whatever. You get sort of confused and you might go to your concentration and come across and then think your absorbance is there, therefore your concentration. You just got to be really careful. You're looking at absorbance, that's a number you get, and then you're trying to find concentration as a result of that, okay? Now, which sample is more accurate? Well, out of the 2, sample 1 is more accurate. And the reason why sample 1 is more accurate is because the data is interpolated. It's between data points. Whereas for sample 2, we had to extrapolate the curve or extend the curve and then find the data off that, right? So sample 1 is within the curve, so it's a better measurement. It's a more accurate measurement of concentration. Sample 2, although it's still okay because, because the trend line's most likely not going to change that much, we don't know that for sure, right? So it's a bit less accurate, okay? So therefore, sample 1's better because it's interpolated data, right? i.e. between data points, versus sample 2, which was extrapolated. So what that means is we had to extend the trend line or our line of best fit, so trend line, and therefore make a prediction off that, okay? So we had to extend our trend line, which is not as accurate. So interpolated data is always better. So that's why you want to pick concentrations where you're going to cover, 1, a wide range of concentrations, and 2, more importantly, cover the concentration that your sample is in. And that can be a bit hard to know, so you would sort of have to do trial and error, okay? Now then, finally, just a couple of notes on our calibration curve. The first one is that you notice we used X to mark data points. So X to mark data points, right? That's just sort of any basic. So that's the same for any sort of basic graph that we draw. Data points always in X if you can, okay? And that's because when you draw the X, ideally that intercept point in the middle should be exactly where your data is, okay? So X to mark data points, always, always. Now, second thing is 0, 0. Do we extend our line of best fit to 0, 0? And the answer is no. So 0, 0 is only used as a data point if it's taken. So only if taken, right? If you notice here in our data, we don't have a 0, 0. So we can't assume that if you have 0 concentration, the absorbance is going to be 0. It should be if we zero the machine correctly, but we don't know if we have or not. So unless you take 0, 0 as a data point, don't extend your line of best fit to 0, 0. Okay, start where your first data point starts, and obviously finish where your last data point finishes. Okay, that's the general rule. All right. The rule with our line of best fit. Okay, so line of best fit again applies to all graphs that we draw, but it's 50% over, 50% under. Okay, 50% over, 50% under. So obviously most of these data points lie in the line of best fit anyway, but if it doesn't and there's a bit of variation or standard deviation, then 50% over, 50% under. Okay, that's the general rule. And then finally, our predictions, we always draw in dotted lines. Okay, so for our predictions, we use dotted lines. And so that's sort of what we've done here, right? So it just shows to the marker that you're actually looking at absorbance and then bringing it down to concentration, right? So anytime you do a prediction, make sure you draw the dotted line on the graph itself to show that you've done a prediction. And especially if you've extrapolated, draw the trend line or the line of best fit in a dotted line, not a solid line, because you actually haven't taken data for that, right? So that's really not part of your line of best fit. Draw it in a dotted line, okay? And so that's quite important, especially in exams. Okay, so to recap the main concepts of colorimeter, because it's quite important because the next spectroscopy method that we'll look at builds on top of this. We essentially take a light source, pass it through a color filter so we only have a specific wavelength or a single color of light. We shine that through a sample, and then we're going to detect how much light has actually been absorbed, okay? And obviously we want it to be the complementary color because that is going to be the wavelength that the sample absorbs the highest, right? But it doesn't necessarily have to be, because like we said, the sample, it absorbs every color except the color that it's showing. So we can put blue there and that's fine. It will absorb a little bit of blue, but it's not as much as it absorbed purple. So the signal is going to be a little bit weaker. So that's why we try to always go with the complementary color. But we'll talk about sort of variations to that in the next spectroscopy method. But the idea is you pass the light through, it's going to absorb some of it, and you detect how much light has sort of ended up passing through. So the higher the concentration, the higher the absorbance of the sample, so the weaker the signal is going to be here. And the lower the concentration, the lower the absorbance, so the stronger the signal is going to be. And so you'll get this output similar to this where you'll get your absorbance numbers. Now, before you can even determine the concentration, you need to create a set of standard solutions to find what the absorbances are for those standard solutions, which you know the concentrations for, and then you plot a calibration curve. So you take your known solutions, find the absorbance, plot your calibration curve, following these sort of main points here, not going through 0, X to mark the spot, line of best fit, etc. And then once you draw your calibration curve, then you can take your sample absorbances, find your absorbance number, draw a dotted line across and see what your concentration is, okay? And interpolated data is always better than extrapolated data, right? Because it's between data points. So that's sort of the basic principles of calorimetry.